Alright, we're going to do this over again. We're going to do this right, since I messed up the video before. Okay, so DeMoivre's theorem and the nth roots. Sorry, I got interrupted. DeMoivre's theorem, yes. Pretty sure that's French. Okay. We may have mentioned this way back in Algebra 2 when we first introduced you to complex numbers. For instance, we talked about 2 plus 3i. But where exactly is that located? Well, to show you the complex number plane, the real axis. Now that's what you've been dealing with your entire life. Whenever we gave you a number line, right? We would say things like, find a 1 on the number line. And you guys, when you were younger, would go, oh. Or find a 2 on the number line, and you would find 2 on that number line. I got a question for you. Did you realize that you were dealing with 2 plus 0i? And the answer is no, you didn't realize that. I mean, you're in elementary school. We just had to put dots on the number line. Well, that was the real axis. The imaginary axis runs through the origin, which is indicated in the picture on the left. So 2 plus 3i is really going 2 units to the right and 3 units up. And there it is. That's the 2 plus 3i. That number sits off the real axis. So, understanding the complex number plane, this is really just kind of like x's and y's. But we're dealing with real numbers on the x-axis and imaginary numbers off. And so we can have complex numbers, a real plus an imaginary, or real minus imaginary, that kind of thing. So, in example 1, plotting complex numbers, we want to plot, they're calling it u, 1 plus 3i. Alright, so yeah, that's 1 over 3 up. There it is, 1 plus 3i. 2 minus I, yeah, that's 2 to the right and 1 down. What do you get when you add them together? Man, this looks very similar to vectors. Boy, it looks exactly the same as vectors. So, the complex number plane and the whole idea of adding and subtracting and multiplying, those kind of things are extremely similar to what we did in the vectors. Okay? So, it's going to look very much the same. But instead of putting 3, 2 with those weird looking vector brackets on it, look how they write it. 3 plus 2i. Did they just add 1 plus 3i and 2 minus 1i together? Of course they did. So, nothing new there. It's a different format. Now, when we say the absolute value of a complex number, we use absolute value bars. Okay. What does absolute value mean? Absolute value means the distance from 0. But in our case, it's the distance from 0 plus 0i, which is kind of like the origin, right? So, if you take a number and ask me, what is the absolute value of 2 plus 3i? Folks, the answer's not 5. Okay? Don't be the kid that says, oh, that's the absolute value of 2 is 2, and absolute value of 3i is 3, and 2 plus 3 is 5. No. Think about what you're saying. 2, 3i, right there. How do I find the distance that it is to the origin? Well, I'm going to guess that you have to use the sides of the triangle. Oh, yeah, this is the Pythagorean theorem, right? So, 2 squared plus 3 squared. So the absolute value is, let's see, 4 plus 9, that's 13. So square root 13, right? That's the length of this. Folks, this is no different than the magnitude of a vector. Why can't I think of the right word? It's no different than the magnitude of the vector. So absolute value of a complex number and magnitude of a vector are figured the exact same way. Now, a vector is a quantity, a physical quantity that heads in a particular direction with a particular magnitude, whereas these are just points on the complex plane. They just have some very similar things. And so, yes, all kinds of cool things are going on. Just like we talked about before. Ooh, the x value, that can be found x equals r cosine theta. Y equals r sine theta. Yes, and so I know they use letters A and B, and the A is the real portion, and the B goes with the imaginary value I. But all of this is being used from the last section. None of this is really all that different. We start getting into the polar form of a complex number. How can you write a plus bi in its polar form? Well, the r and the theta, right, of a polar coordinate, r comma theta. Now, as I've said in the notes, we use brackets. I don't know why Math Excel uses parentheses. Makes no sense to me. But the r and the theta of a polar form coordinate, well, that can't be that bad, right? So we have r cosine theta plus r sine theta I. That's the whole a plus bi, right? But what can you pull out of both of those? What do they both have in common? They both, just like we've seen in previous questions, or something similar to it in section 6.4, they both have an r in common, and we can pull that out. And so that's going to leave us with cosine theta plus. Now, don't ask me why they do this, but they like to put the I in front. So they say I sine theta. I think it's so that we don't, think that I goes with theta. I think that that's kind of the reason why they do that. But it's certainly, when we actually put in values for sine theta and cosine theta, we'll see that the I goes after. But anyway, so we already know how to find theta. Theta is going to be found by inverse tangent, using B and A, the rise and the run, just like the stuff we've done with vectors. So let's look here at example 2. Use an algebraic method to find the polar form that goes from 0 to 2 pi for this complex number. Okay. So 1 and minus radical 3 I. Excuse me. Now radical 3, we know that's approximately 1.73 for those of you decimal fans out there. So I'm going to estimate that the dot is right about there. Okay. So we are going to be doing our little rotation down to here, and then we're going to march forward to find that. It does say that theta is a positive angle. Now you might say to yourself, well, couldn't we just use the negative angle? Well, if they hadn't put that stipulation on theta, then the answer is yes, we could have. But since they threw that stipulation in there, no, we can't. However, we do have a cool little right triangle here that we need to think about. It's got 1 and radical 3. Now, I know you can say the negative, right, because it's going down, but the truth of the matter is the length of it is radical 3. Now, you probably should recognize that cool triangle because that is a 30, 60, 90 right triangle. And we're going to find the angle theta, which is this red one in here. But we're going to do the inverse tangent, right? Inverse tangent of, we're just going to use the positive radical 3, opposite over adjacent. And of course, let's see, make sure our calculator, I don't think we need this, but you know, let's just say we did. Make sure our calculator is in degree mode. Invert the tangent of the square root of 3. Dividing by 1 is not all that important. And we get 60 degrees. So inside that triangle, and let me maybe blow up a version of that. Inside that triangle is a 60-degree angle. Which means that the blue angle that I'm interested in, the one all the way around there, would be found by taking 360 and subtracting that 60-degree angle. So that's a 300-degree angle. So in my final answer, I know that 300 degrees is going to be the polar portion. Okay. And then the radius. Ooh, the radius, that would be the hypotenuse of that right triangle. And so we could do, if we didn't already know that it was 2 in length because it's a 30, 60, 90 right triangle, and you take the short leg and you double it to find the hypotenuse, if you didn't know that, we would do 1 squared plus radical 3 squared. And of course, we would take the square root, right? That's the square root of 4, which is 2. So, knowing that the hypotenuse is 2, that's 2. Now, do we need to write that in its polar form? I mean, I'm sorry, into the complex number in its polar form? Sure. In other words, we need to write it in the form that you see right there. So, its polar form, z, would be 2 cosine 300 plus I sine 300. And that would be our final answer for that. And that is 300. So, sorry, that was a bad looking 0 right there. Try to do a better one. There we go. That's a little bit better. Okay, so what's it going to look like for the other one here? So we are dealing with, so -3 and -4i is right about there. And we can look at the triangle that's formed like that. All right, we've got 3 on this side and 4 on this side. Yes, I know they're going in the negative direction. It's important that I note that, especially for the angle that I'm going to find. Oh, and by the way, sorry, I did everything in degree on the last one. You know what? We're just going to stick to degrees for these questions because I know a lot. I mean, could I change that last question and use, 5 pi over 3? Could we have written that 2 cosine 5 pi over 3 plus I sine 5 pi over 3? Sure, I could have. But for argument's sake, I think what we're going to try to do is we're going to try to stick to degree measures for a lot of these questions. So let's see here. If hopefully you already recognize that's a 3, 4, 5 right triangle, from all the work you've done over the years, that's a nice Pythagorean triple. But suppose you don't, then we're going to a little 3 squared plus 4 squared, take the square root. Tells me that we're dealing with the square root of 25. 9 plus 16 is 25, so that's a 5. So that is your R value. That's the radius. We do need to invert the tangent. Let's pick a different color here. Invert the tangent of opposite, right, over adjacent. And if I invert the tangent, hold on a second. Okay, so invert tangent 4 divided by 3, and I get 53.1 degrees. Okay. So if that's 53.1 degrees, then what is the rotation that goes from here all the way to there? Wouldn't it be 180 plus 53.1 degrees? The picture is important, folks, because if you don't have the picture, you won't know which quadrant you're in. I don't want to hear you say, well, do we always add to 180? Only if you're down in quadrant 3. If you're up in quadrant 2, you would subtract from 180. If you're in quadrant 4, you'd subtract from 360. If you're in quadrant 1, you don't do anything at all because you already have the angle. Look at the picture to be able to tell what you're going to do with that reference angle. So now we know the theta. All right. So I might have to scroll down here. So in this case, the z in this case would be 5 cosine 53.1 degrees plus I sine 53.1 degrees. Why did I say 53.1? I just got done saying we would do something with that. Gee whiz, I can't even listen to myself. This is ridiculous. 233.1, 233.1 degrees. Man, it'd be really cool if I could listen to my own self. Of course, I can listen to my own self. I haven't lost all my hearing, as some of you know. Multiplication and division. We can actually multiply and divide these complex numbers, and it's not as bad as you think, really. So we actually have this pretty cool strategy on doing this. If you want to multiply them together, you first start by multiplying the two radii together. And then you add the angle measurements. Piece of cake. What do you think we're going to do for division? Exactly the opposite. We're going to divide the radii. Then we're going to subtract the two angle measurements. It's really pretty straightforward and easy. And just to make your life a little bit easier, why don't we just convert them to degrees? Right? So 25 radical 2 cosine negative 45 degrees plus I sine negative 45 degrees. Here, I'll just put negative 45 degrees. And 14 times cosine 60 plus I sine 60. Use an algebraic method to express the product of z1 and z2 in standard form. Okay, so 25 radical 2 times 14 is going to be 350 radical 2. All I'm doing is multiplying these two things together. And then we add the angles, and negative 45 and 60. Negative 45 and 60 add up to 15 degrees. So now they did say back up here in the that approximate exact values with a calculator when appropriate. I don't know why you're approximating exact values with a calculator. Oh, I see what they mean. They mean put in decimals. I thought they were talking about radicals, and I'm like, why would we approximate? Anyway. Cosine 15, we could do something with radicals if we wanted to go back to half angles, but there ain't no way we're going back to that to throw that in this particular situation. So we really just need to use our calculator. The cosine of 15, that's going to be like 0.966 plus I, and then the sine of 15 is 0.259, something like that. And then, of course, we're multiplying this by 350 radical 2. So if I just took 350 times radical 2 times the cosine of 15. That would do it all for me at the same time. And so, basically taking this times that, 478. Oops, I can't even write. I bet I can't get rid of that decimal. Oh, I did. Thank you. 478.1. That's good enough. Plus, and then 350 times radical 2 in parentheses sine 15. 128.1. And as I said before, when we write them in this form, we always put the I at the end. I know they put the I in front of it when they're doing this part right here, but that's only so you don't think we're taking the sine of 15i, an imaginary number, which, talk about crazy. Okay, so it really isn't too bad. We multiplied the radii together. We added the angle measurements, and then we threw it in a calculator. Example 4. So same thing. This time they want me to divide. So Z1 over Z2, that's the way they have written it. Z1 over Z2. And so according to what we saw, we would take the radius of the first divided by the radius of the second. And then we're going to end up subtracting these two angles in that order. So what is 135 minus 300? That's going to give me definitely a negative angle. 135 minus 300, negative 165. So we've got cosine negative 165 plus I sine negative 165. I don't know, maybe we should throw some parentheses in there for kicks and giggles. And of course, degrees. So it's time to throw it in a machine now. Obviously, you can reduce that first part to radical 2 over 3. Not to be confused with radical 3 over 2. Totally different. So yeah, we could reduce that to radical 2 over 3. And the square root of 2. If you're going to do that in a calculator, you want to put parentheses after radical 2 and then hit the division key. So, that's like this part right here is 0.471, just that part alone right there. And then, of course, that thing, you know what? You can use in your calculator, if you want to use the store feature, it's right above the on button. It says STO, and it has an arrow. I'm going to use that store button, and then I'm going to choose the letter A, which is right below the alpha button. You do have to use the alpha button and then hit the math button so that it says something like this. Mine says answer. I guess mine says answer. And then has this and then this. That way, it's now stored in that location. So what I can do then is I can tell my calculator A times cosine negative 165. And if I take that A value and multiply the cosine of negative 165, calculator gives me. And you should double check this to make sure you can get the same result. I don't know why I need a comma, because we're writing as a complex number. And then alpha A times the sine of negative 165. Just remember that alpha A that I'm using, that's just a storage location. If you want to type radical 2 over 3, or radical 2, and then divide that by 3 and get that 0.471 number, and then multiply that times this, you're more than welcome to. I got negative 0.122i. So negative 0.455 minus 0.122i. There is your complex number for what do you get when you divide them. Now, powers of complex numbers. This is DeMoivre's theorem. Okay. Yes, you want to say it with emphasis so you sound cool. So, what do you get when you take one of these complex numbers and raise it to a power? Well, DeMoivre proved that when you take one of these complex numbers and you raise it to a particular power, then the only effect it has is it takes the radius and raises it to that power, and it multiplies the theta values by that power. Interesting. So, what happens when you take 1 plus I radical 3 and raise it to the third power? Okay, well they show in the picture, of course they found the radius, right? 1 squared plus radical 3 squared, and take the square root, right? We've done that before. Obviously that gives us square root of 4, which is 2. Now, oops. So we need that. We also need the theta, right? So we're going to do a little inverse tangent, radical 3 over 1. That gives us our 60-degree measure. And now, how does that 3 on the outside, what does that do to the graph? Well, it takes the radius and it raises it to that power times the cosine of, so we've got our 60-degree angle, and now we're going to triple that 60-degree angle. So as you can tell, that's 8. All right, 2 to the third is 8. Cosine of 180 plus I sine 180. Well, those are nice numbers. 180 is over here on the unit circle, right? So what's the x value out here at the outside edge of the unit circle? Isn't that -1? So that would be 8 times -1, and the y value at that spot on the unit circle, isn't that 0? So that's I times 0. So you're telling me this is just -8? Yes. We took an imaginary number and raised it to the third power, and we ended up with a real number, -8. Dun dun dun! That's the weird crap that goes on with the complex numbers. You can take powers and end up with real numbers. That is weird. You can't do that with real numbers. You do that with a real number, you end up with a real number. But this is kind of weird. You can start with a complex number, not even on the complex plane, and end up with something on the real axis. Whoa, that's cool. Okay. Why in the world was the word home written there? Oh, that's on my notes, my permanent notes. I guess that's home. Weird. Okay, so using DeMoivre's theorem, we're going to do the same type of thing here. So we've got, and folks, I would never write it like this. Negative radical 2 over 2 plus I radical 2 over 2, all raised to the 8th power. Okay? So where is that on our coordinate system? So we got negative radical 2 over 2, positive radical 2 over 2. Okay. And so that's about like, you know, so negative, here's -1, here's -2. Like that's +1, +2, something like that. Because, you know, radical 2 over 2, we know radical 2 over 2 is approximately 1.414 for those of you decimal fans out there. We're in quadrant 2 because we went left and up. All right, so we need to look at this triangle. It is a 45, 45, 90 right triangle. For those of you who can kind of see that the opposite and adjacent sides are exactly the same length. But if you didn't know that, we can do the whole tangent inverse of radical 2 over 2 opposite over adjacent, which is tangent inverse of 1. And we should all be able to tell that that's a 45-degree angle inside here. Okay. Sorry, I thought I messed up before. But to use DeMoivre's theorem, I'm going to have to find this angle right here. Well, if inside the triangle's 45, then that means this has to be 135. Okay? That makes sense. And if we do the whole radical 2 over 2 squared plus radical 2 over 2 squared. Take the square root, you know, to find the radius. That would be 2 over 4 plus 2 over 4. Oh my goodness, that's 4 over 4, which is the square root of 1, which is just plain old 1. That means it was, hypotenuse of 1, or radius in this case. You can call it the radius. Okay, all right. So we're dealing with 1 cosine 135 plus I sine 135. And now we're taking this thing and we're raising it to the 8th power. So the first thing we had to do was we had to convert this. Now, some of you might ask, well, why the heck would we want to do that? Well, this is a shorts. I mean, if you raise something to the 8th power, don't you have to multiply it times itself 8 times? Who wants to do all that binomial foiling? Nobody. That's why this is useful, changing it to its polar form. And then DeMoivre's theorem allows me to take the radius and raise it to the 8th power times the cosine of whatever 8 times 135 is, which we'll figure that out in a second, plus I sine 8 times 135. Okay, so now 1 to the 8th. I'm really hoping that you guys know how to do that. 8 times 135, that is 1080. Because that's just a plain old 1, so that's pretty boring. Please don't be the kid at a party that says, distribute the 1. Don't do it. Those people get made fun of. And I don't want that to happen to you. Cosine 1080. Ooh, where is 1080? 1080, is that a multiple of 360? It is! Why didn't I remember that? It's 3 times around the circle. 1080 is sitting smack dab over here. That's 1080. So of course the cosine is 1. And the sine. What's the sine of? That's the y value, right? So we have cosine is x, which is a 1, and the y value is 0. Oh my goodness. The answer to this question was 1? Yep, folks, that's true. When you took that thing and you raised it to the 8th power, you got a 1. Now, those are the examples that we're focusing on in this section. There are other examples of things that we are not going to cover in this chapter. So those are the important things, and I apologize for messing up the video, and hopefully you get to watch this one instead of my other ones. Thank you very much. You can watch the other ones if you want. I did see one mistake in one of them, which you can use this one to find.